Hello, I'm Awesome Mealy and I'll be presenting my project, Solving Goishi Hiroi with a Genetic Algorithm Utilizing Wisdom of the Crowd. This is for CSE 545, Section 50, Fall 2024. To begin, let's discuss what Goishi Hiroi is. Also known as Hiromono, this is a Japanese variant of peg solitaire. Perhaps you've seen the puzzle where pegs fill a board with one empty hole, and the goal of the game is to hop pegs over each other, allowing you to remove the hopped peg until only one is remaining. Well, Goishi Hiroi is a similar logic puzzle, but it's performed on a Go board pictured on the right. The objective is to pick up all the stones on the board one at a time by performing certain legal moves. To play, you pick a starting stone, then to move to another stone, you must go to the first stone within a vertical or horizontal axis. Every time you move to a stone, you pick it up and continue where you left off. The only stipulation is that you can't perform a U-turn, coming back in the direction that you just came from. And I'll go through an example here with this board. So essentially what we would do is we would pick a starting stone and we could go horizontally and vertically, and each time I move to a different stone, I'm essentially picking it up off the board so I can't traverse it again. And we just keep completing legal moves, and then if you notice, I can't go up because then I'm sort of trapped on this stone, but I've already made a mistake because this stone no longer has someone to go to. So I could continue down here, jumping over to the right and up, but then I go into a similar spot where these stones are sort of unable to begin gone to. So we could start coming in from these stones and then creating a solution kind of backwards. But this comes to a problem where this stone has already been picked up. So how would that solution work? We could come back to this later, but that's essentially how this puzzle is played. And now, where does that come in with the topic of artificial intelligence? Well, it's to answer the question, is this board solvable? This question is very similar to a Hamiltonian path problem, where given a map of different nodes with certain connections between them, the question is, can you visit each node once? This problem adds some nuance with what it determines as a legal move. But the goal of this project was to write an algorithm to solve various board states by providing a valid trip across the board or deeming that board was unsolvable. This fits with an NP complete problem. The answer is hard to come through. You have to consider a plethora of different options. But once you give an answer, it's very trivial to prove that it's correct or incorrect. So with that being said, let's approach how that was done in this project. This project centers around a genetic algorithm. Now, this algorithm, aptly named, is comparable to natural selection or biological evolution. Creating a genetic algorithm means implementing each of the following listed here, defining a population, selecting the best performers of that population, creating a way to use those performers to make the next generation, and a mutation process. An added feature in this project is elitism that I'll be going over later. So, to begin setting up the genetic algorithm, first we have to define our population. Setting up the data for an individual answer is important, as all the following features are reliant on how you manipulate individual answers. For our problem here, realize that this is a graph traversal problem. So that means each individual answer can be a string denoting which stones have been picked up in the specific order. And with that simple setup for each node, generating our first population is fairly easy, as we just fill up the population up with random answers. I limited the generation of answers to having every stone listed, so each trip has every stone with no duplicates. Now, this would be a potential valid answer in a graph traversal problem where every node is connected, but like a traveling salesman problem. But the problem we're facing here is different, where we can't just hop from any stone to any stone. But that doesn't really prove a problem in defining the original population. Because remember, the goal of the algorithm is to find out if the overall board state is solvable or not. So it's to be expected that the genetic algorithm will be running over and thinking about a lot of incorrect solutions in the hopes that over each generation it hones in on an answer. The next is a selection process. So now that we have a population filled up, we have the luxury of picking out the best performers to create the next generation. The key here is to create an evaluation function that's to be applied to every single node. And that evaluation function should be tailored to the problem at hand, higher scores being those that are closer and closer to our ideal search target. For the puzzle here, we want to answer if the board's solvable. And to be solvable, you could restate that as you want to produce a trip with all valid moves. So in that vein of thought, the evaluation function I chose was to count the legal moves a given trip has. This constitutes going over each pair of consecutive stones in a trip and reading the graph to tell if that one single jump was legal or not. And once this process is completed for the entire trip, that node is labeled with their valid move count. The idea here is that solutions with higher valid moves will have stones next to each other in their trip that would probably exist in our final ideal solution. And so we keep those nodes that have consecutive right stones, and over time, over generations, hopefully we stumble upon a node that has all valid moves in it. So once we select the two best nodes, we go to the problem of birds and the bees of how do you make children out of parents. So the early stipulation, in which we created our population, should be kept through the generation or combination process. So remember, I wanted all the children to have every stone represented exactly once. For a combination method, we need to merge the parents together somehow. So for a traversal problem, the obvious holdback is that just splicing the two parents together doesn't really work because you could have duplicates or missing stones in our case here. In order to get around this, I used a modified uniform crossover. So a uniform crossover is where each element of a trip is chosen from either parent with an equal probability. So on the right, you can see a breakdown. Beginning at the top, you can see that I have a randomly generated mask of zeros and ones on the top left, and then on the right is just the inverse of that mask. Each mask, it creates a respective child, and for each one in the mask, I'm selecting the element in the same position as parent one. So if I can... So for these two ones, I'm picking C and D, B and C from parent one for child one, and then on the inverse mask, I'm picking A, skipping 2, and then picking D and E. And I filled that out completely for each child. Then you go back over and handle the zeros. And the zeros signify that we are now pulling elements from parent 2. So you can see here, the first zero, we're picking the first element we run into on parent 2 that was not already in child 1. Thus, we kind of have to run over each child twice to generate them. But either way, we can see that we're going to grab the first element. We check if that's already in the child. F is, so we get K. And then we've begin filling that out. K is already here. A isn't. Throw that in. And then we complete child 1 and we complete child 2. So when this process is completed, we produce two children that contain some elements similar to the parents, as seen whenever they are sequences of the same digit in the mask. Each time a pair of children is to be generated, a new mask is created. And the hope is that these masks not only create valid children, but in terms of unique stones in the answer, but that we have a chance to keep all legal moves and find new ones. So now that we've just created an entire generation of children, we can't really walk away. There are two extra steps tacked on before repeating the selection process again. The first is elitism. So this refers to pruning the next generation to remove overly poor performers. So the hope is that removal will help the algorithm hone in on an answer rather than reconsidering poor options. So my implementation in this project involved finding every child that performed worse than either of the two parents, meaning that it had less valid moves in the path that it came up with, and just replace them with a parent. This means that the overall evaluation score of a population should either stay the same or get higher. Now, the risk here is that if the population becomes too homogeneous, then we end up cornering ourselves in we could corner ourselves in a local maxima on the solution space. So to combat this, we have mutation as a final step of our generation process. So this involves going over each element of a trip and having a flat chance that something will change. So this helps let us take small steps around after taking giant leaps earlier with the combination method. My implementation here, it was when an element was picked to mutate within a trip, a random other element within that trip would swap places with it, thus creating another valid answer where each stone was only represented one time. So another way to make sure we get as many solutions as possible, mutation helped us get a little bit more diversity. But here we're using the wisdom of the crowd effect. So that can be explained as the collective opinion of a group can often be better than any individual person in that group. So for our efforts here, this means grabbing answers from different runs of the genetic algorithm and then combining them. The reason I'm going so far as to run the genetic algorithm over and over again and then combining those answers is that, remember, the initial population is completely random. So this means that each run of the algorithm hones in on its own solution within the solution space, and when we combine all of them, we just have a wider berth of information to pick from. So when we get all the answers, we have to make a smarter combination process than the one the genetic algorithm uses, because here we want to begin eliminating randomness and actually taking as much information as we can from the answers that we are looking at currently. So for this project, I selected the top performers of the pool of answers, and I dubbed them the elites. These elites were then examined to create a voting system, and each one of the valid moves within a trip, so any set of two stones in either direction, was added to a table for how many times it showed up in each trip of the elites. So now we have a bunch of votes on what to do when we start at any stone. To create the final solution, I made a group of answers, each one starting at a different stone, and then let the voting process fill out the rest of the path. And the best of those answers was then deemed the wisest answer the algorithm could produce. So ideally, this final answer will be a yes or no on if the puzzle was solvable or not. And that sort of bridges us into the results of the project. There are a couple different parameters to set in the algorithm. There's population size, mutation chance, how many generations to create, how big of a pool of answers should there be, and from that pool, how many elites should you pick. So here is a testing on one data set, a 9x9 grid with 20 stones. And I was trying to find the best expert percentage or elite percentage to pick for that pool of answers. So since there are 20 stones on this board, that would mean the ideal answer would be 19 moves. As you see, with higher elite percentages, we started to get results that were closer to our ideal solution. You can see in the wisdom result column, we were getting 17 multiple times. Remember, the goal is 19. So with that being the case, with the higher expert percentages giving a better result, but the minimum was different with the expert percentage of 30, that gave the most confidence in that percentage being the set parameter to use in this project. So with confidence comes disappointment. As we can see, here are the results of running the full algorithm with the wisdom effect tacked on afterwards. So the off from ideal column on the right shows the difference between the algorithm's answer and the ideal best solution. You can see for the smaller data sets, we were only off by 1 or 2, but as the problem grew in size, not only for the board but also upping the stone count, we started getting way off our ideal target. The max hit column denotes how many times the best evaluation came from the genetic algorithm. So on the minimum and maximum, how many times did it just running a genetic algorithm give us that maximum for each generation? Looking at bigger boards with more stones, the time executed for one run, as well as the relative accuracy, quickly became unwieldy. Note how the answers for 70 and 100 stones were almost the same. So if this project were to be continued, I would take another swing at creating the evaluation function. While the number of valid moves seems like a good idea for a trip, it fails to consider when do those moves take place, and the end result is looking for a string of all valid moves, but you have to consider where you started in the first place. In addition, the combination process, as I have it here, routinely breaks up the sequence of valid moves, meaning that even though the performance of each generation should get better, it ended up being very unpredictable, as we can see on the next slide. Ideally, a genetic algorithm would produce results something like this, where on this same graph, every generation, it would start getting better and better with more valid moves showing up. But that clearly was not the case. This result shows that it was really a mixed bag. Each generation highly unpredictable from the last one. That being the case, note that the dashed line at the top of the graph. The red line is the ideal correct solution, and the blue line is the result of the wisdom of the crowd approach. So this pattern shown here held true for every data set. Sampling the elites from this mess of a family tree would always yield a better answer. So both of these graphs were done on the 6x4 data set that was shown at the beginning of the presentation. And if you look at the right side of the grid, the right grid, it's the solution, or one of the solutions that the algorithm ended up coming up with. So seeing this shows that it only had one illegal move, that diagonal jump. Now, even though the algorithm wasn't able to evaluate if it was legal or not, which it is, this does give users a chance to see the areas of improvement. In examples where we could add new stones, we know exactly where to place it. And in examples where we still try to solve the problem, outputting multiple runs with charts like this can give us a good field of options that we can then iterate through and with light touch-ups to find our own solution. For example, this solution, which was very hard for the algorithm to end up coming up with, but there's in fact only one unique solution to this, and it's starting here, jumping, and then since these two stones have been picked up, this is now a valid move, which I think that jump never comes up as a valid move in the voting system, as valid moves, these would be the valid moves that would show up in the elites. So in further work, a way to capture this long elongated jump would hopefully yield a better result for the project. So that concludes my project. It was an interesting foray into writing an algorithm like this, and I'm hoping the result doesn't take away from the takeaways from working on the project. Thank you very much for watching.